the learning objective of the session is we look at basic principles of networked control system on board vessels. We look at what is called communication protocols, and we look at what are interfacing and wiring standards. If you look at the way automation is developed in the industry, even on-board vessels, initially we had relay-based control, which is called as hardwired relay-based control, where you'll have push buttons, relays, sensors, pressure switches, pressure transmitters. All these will be connected by wires. And the entire control system works on allowing current to flow through the circuit or by interrupting the flow of current. This type of system is called as relay-based control, and it is called hardwired because it works in only a particular way. And the wiring and the components that are used will decide the logic. The word logic is simple. Logic means what will happen, the particular way in which a control circuit will function. That is called logic. So a small diagram is here. You can see this is a symbol for a relay coil. When the coil gets energized, contacts will operate. This contact is shown here. You have all these are relay coils, and these are contacts, and they're all wired together physically by electrical wires. This table here shows what will happen next if this coil gets energized, what will happen and which line you should go to. For example, if it says 75 here, you should see 75 here, and you can see a same contact of this coil, the contact will be here. So this is the meaning of relay-based control, which is very much there even now. Then we moved on to programmable logic control. A lot of vessels have PLCs for a very long time. In a programmable logic control, the logic is not in the wiring. This is the major difference. As the word says, is the logic is in the program, and the program itself is stored inside the PLC. And a PLC has a separate input side and an output side. If you take a picture here, look at the picture here, you can see this, that on one side you have the input device, on the other side you have the output devices. Input devices will be push buttons, pressure transmitter, temperature transmitters, level switches, all these, which will give signal to the controller. Output devices will be solenoid valves, motor starters, alarm buttons, alarm lamps. All those will come on the output device. And there is no direct connection between these two. Instead, what happens is this input device will give a signal. The CPU runs a program. The program has to be written and stored in the memory. And when the CPU runs the program, it will take decisions. If you push a push button here and the bulb has to glow on this side, then you have to write a program to tell the CPU that if a button is pressed here, you must energize a bulb on this side. This is the way the PLC works. And the idea of a PLC came from observing human beings. We are all PLCs, and very advanced PLCs, obviously. So do we have input modules? Do we have input sites that you have? This is the input module. So from here we get our ear. And our brain is the CPU. Memory is also the brain. And what we do is we just run programs. Right now, I'm running a program called lecture program, and all the rest in the group are running a program called the student program. Once this lecture is over, we'll shift to another program. So the same human being is capable of running different for the day. So that is how this idea of a PLC come from. Now what has happened is this has moved to a next level where you have supervisory control. That means it is called SCADA. SCADA stands for Supervisory Control and Data Acquisition. What happens here is that you have controllers in the field. That means you'll have a jacket pulling water controller in the engine room. You'll have another controller for lube oil temperature. These controllers will be connected to an HMI. HMI is a human machine interface where an operator will sit in front of a computer and he can interact with the system. Now you have systems where from one computer you can control different processes. You also have systems nowadays where many computers will run a single plant. You will see examples of these. And now what you are seeing is this is the third or fourth level of control that you are seeing, that controllers, sensors, actuators are all connected together in networks. Often there is no distinct input side and output side. All are connected on the same side. So we have to see how this kind of control is possible. To start with, you have to have a brief comparison of what is analog and what is digital. Analog signals are continuous signals. Usually, if you take an example of current as a signal, and if you take a flow transmitter as an example, this flow transmitter has got a measuring range of 0 to 400 cubic meters per hour. Right now, there is a flow of 300 cubic meters per hour. This 300 cubic meters per hour will be turned into a 16 milliampere DC current. Because these controllers, many of you know, these transmitters have a normal 4 to 20 milliamperes output range. So 16 milliampere of DC current will be continuously flowing through this circuit. This is an analog signal which is continuously available. If it is a digital signal, it will turn into a series of voltage pulses. The same flow will be turned into, first of all, analog signal will be generated. It will be turned into series of voltage pulse. These pulses together will say the flow rate is 300 cubic meter per hour. So the advantage of turning into this we will be seeing, but one simple advantage is, whereas this current will be a continuous flow, this will be, you have a choice. Do I want to keep on sending it as the signal, or do I stop and start again? So it is easy to send it in packets. Because of this ability, there is a big advancement in the way network control systems develop. So if you see this, analog signals, if you take 4 to 20 milliamperes as an example, they are continuous signals, and multiple analog signals cannot be transmitted in the same wire at the same time. You cannot transmit two DC currents in the same wire at the same time because you cannot separate it. You can send one DC and one AC, but multiple AC currents in the same wire are difficult to send unless you send them at different frequencies. Then you have to separate the frequencies once again. So it is not easy or possible to send multiple analog signals in the same wire at the same time. But digital signals are made up of two state conditions. In fact, the word digital comes from digit. Digit actually means finger. So if you raise your finger, you are telling something, and if you lower your finger, you are telling something else. 0 or 1, you say dot, dash, you say 5 volts, 0 volts. These are all examples of two state conditions. And in digital signaling, this is the way you work. You just use a two state condition and you can transmit information. And one of the easiest and early examples of digital communication is Morse code. All of us know what is Morse code, that with just two dit and dat, two states, it is possible to send alphabets, you can send numbers, anything you can send. So what has happened now is that any source of information, whether it is text, whether it is picture, image, number, symbols, all of it can be turned into equivalent 0 and 1. And 0 and 1 will be turned into a voltage pulse. So a 5-volt pulse will be 1, and no volt will be turned into 0, will represent 0. That is the way digital signaling takes place. So if I want to transmit a jacket cooling water temperature is at 85 degrees, if you want to say like that, now I will send it as a series of voltage pulse instead of a continuous current. Now because it's a set of pulse, it can have a beginning and end. This gives a lot of advantage in ability to transmit signal. One of its biggest advantages, it is possible to send multiple signals in the same wire if you do it in control. Basically, you have to do it turn by turn. You need not send all at the same time, but you can take turns and send the signal. Because of this, there is a big difference in the way control happens. This is a brief look at the ME engine's control system. We'll come back to this screen again at the end. But to see it first, it is like this. In the ME engine, which is camshaftless, the main engine is controlled by many MPCs or multi-purpose controllers. Each of this is a multi-purpose controller. This is called cylinder control unit. This is cylinder control unit. This is called auxiliary control unit. And each of this is actually a computer. It doesn't have a keyboard or a display, but it is actually a computer. And input signals come from different sensors, and outputs go to different solenoids, and all these are connected together by a network. It's a redundant network because it is, even if one fails, other will take care. Now each cylinder is controlled by a CCU, and all these controllers are controlled by ECU, which is called as a master controller. ECU is the master controller, CCUs are called slave controllers, and this whole thing runs on a network. If you look at Artiflex engine from Wärtsilä, it is like this. Here each cylinder is controlled by a module called FCM. It's called Flex Control Module. Here there is no controller above these. There is no master controller above these controllers. And this works on a bus called a CAN bus. It's called CAN stands for Control Area Network Bus. So these are all examples. So if you see this screen together, if you have a 6-cylinder engine, these are the 6 FCMs. This is called an online spare, which also will be present. Now all these black lines are going to each cylinder. This is for one particular cylinder. And signals come from sensors like this through the network. You can connect your control panel here, alarm monitoring system, all these are controlled. And you'll see this, it says scan open module or Modbus. This is what we are going to be talking about. What are the meaning of these? Or you can take a look at this. This is an example of a monitoring and control system from Terasaki. It works through Ethernet. And in the ECR, the engineer can sit and monitor all the events from signals which come from input device. If you take an example like a level alarm, bilge level alarm is there. Then that input comes through this. This is the Ethernet. And for sitting here, the operator can activate the pump. So you don't have to go to the pump control stand to start it. You don't have to, from here we can do. So all this, many of the engineers have already seen on board ship. So what we are saying is this application has already been there. The purpose of this lecture is to look at the background to this. What is behind this kind of control system? So how do these networks function? What is the difference about this compared to other one? It is something like this. A PLC is similar to a single human being. We do different things by executing different programs. A network control, you can say, will be similar to a group of human beings who are going to communicate and getting things done. So a PLC is a single human being. A network control is a group of human beings. If you start with that, you will understand the issues which are there. In any kind of communication, you need transmitters and receiver. So for a human being, the mouth and the voice box is the transmitter, and the ear is the receiver. So if communication has to happen, then all of us understand this. Two transmitters cannot communicate to each other. Two receivers cannot communicate to each other. If you want one-way communication, one transmitter and one receiver is enough. If you want two-way communication, then you need both. So we are called duplex system. Duplex means we have transmitter and receiver. Similarly, you will have devices which are called simplex device. If it's a simplex device, it is only a transmitter or a receiver. If it's a duplex device, it is capable of doing both. So, for example, you will think a pressure transmitter it's only a transmitter. It is only giving signal. It will be called as a simplex device. A solenoid valve is a simplex device. It only accepts command from the controller. But nowadays, you will see examples where a solenoid valve is also a duplex. It takes order from the controller. It also gives a feedback to the controller about its position. So you will see examples where what was considered as a simplex device are now replaced by duplex device. So this is the meaning. Duplex means it can transmit and receive. Now, if human beings communicate, then what are the issues that are here? How do we know who is talking if there is verbal communication? Identity of the person is known. That identity is called as address. There are many ways of knowing the address. If you make a phone call, the phone number gives an address. Then in any kind of verbal communication, there are some rules which you have to follow. One of the two important and simple rules are the same language must be used, and then usually one person should talk at a time. So this is the set of rules of communication. Same way, if you see, these rules are called as protocols. And same way in control systems also, or in network control also, you need to have protocols. And these few are examples of this. One is called Modbus, another is called CAN bus, another is called Profibus. You have DeviceNet. There are many such examples of protocols are there. The protocol basically lay down the rules of how the communication should take place. They prescribe the format in which the communication has to be sent. So, for example, if you look at human language, if somebody speaks to us in Japanese, then we are not able to understand. It is not because our ear is not working or the brain is not working. It is because that format of the sound has not been understood. So similarly, if signals are sent through a wire, that signal will be always in either current or voltage pulse. But that format still has to be understood. Unless the format is understood, the signal will make no sense. The format is controlled by what protocol the system works with. So this is one of the important principles. There will be protocols. And you can very loosely understand protocol similar to this. Rules and the format. Then one more important thing is communication must be in discrete packets. It means beginning and end, not continuously. So what this basically means is that if I connect my devices, what we mean by devices, sensors, output devices and controllers, all will have address or an identity. And devices will communicate as and when required and not all at the same time. So if you control these, then it is possible to simplify communication, and that is what network control is all about. So to repeat, this is the first thing. All devices must have address. And then the way the devices communicate has to be controlled. And all will not speak at the same time. All will not keep on talking at the same time. There is a control over how the communication takes. So based on this, it is possible to have this advanced control system which we have now. One more important principle is called interfacing and wiring standard. Ethernet is an interfacing standard. Ethernet is very well known. It is widely used for computer LANs everywhere. RS-485 is another industrial LAN widely used. These two are very widely used in industries now. RS-232 is called as a point-to-point interface standard from one device to another standard. USB everybody knows. USB is also available in industrial applications nowadays. So all these relate to how the connectors are arranged, number of wires that are used, the voltage levels that are used. All these are controlled by these wiring standards. Nowadays there are converters.
Mr. Venkatesan, if you want 5 minutes notice, please. 5 minutes.
Yes, okay. Thank you. So nowadays we have these converters which are capable of going from connecting from one wiring standard to another wiring standard. Now, one more important thing to understand is in all these communication, you should have, there are two types of communication system. One is called a half duplex system. Half duplex means it will transmit or receive only one at a time. And a good example is walkie-talkie. Walkie-talkies, we can talk and listen, but you cannot do at the same time. So that is called as half duplex. Full duplex means it can transmit and receive both at the same time. And mobile phone is a good example of this. So depending on which type of system is there, you can set up these. RS-485 is a widely used network system. We can see here up to 32 controllers or even more can be connected. It is capable of connecting up to even 1200 meters, and it can be in half duplex with a 2-wire system. This is a 2-wire system. It will work in half duplex. Or if you put a full duplex mode, it will work with 4-wire system. So that means the devices can communicate up and down simultaneously through two different wires. 2 wires, 2 for receiving. Now, if you after looking at this, if you come back to the same screen again, now you can understand that each controller cylinder is controlled by a CCU, but the CCU will not do what it wants. It has to be controlled by the engine control unit. This is the master controller. ECU is the governor. So you have this arrangement of one master controller and these are slave controllers. And Modbus, Profibus, all these use this master-slave type of control arrangement. So you have this redundant bus system. Sensors give their inputs to all these. And as we said before, the sensors will communicate not continuously. They don't use the same wire. They will keep sending turn by turn the information. Same way, if you go back to RTFlex, it is like this. In the RTFlex, it uses control area network. This is called as peer-to-peer protocol. That means all are equal. There is no boss over this. In this case, the governor function is distributed. That all these units take care of maintaining the RPM. So RTFlex is different and ME engine is different. Now MEB is also got a variation in this. So this shows the CAN bus or the Modbus module which can be used. So to summarize, these are the few points. Wiring becomes extremely reduced because you in the relay-based control, each device will use a wire exclusively. Nobody else can use that wire because it will be transmitting continuously. In these systems, the transmission is not continuous. Because of this, same wire can be used to connect many devices together. Like you saw the example, just with 2 wires, you can connect 32 devices. In some application, you can connect even 256 devices just with 2 wires. And all these can be controllers, input device or output device. You can connect them all together without wiring becomes extremely simple and inexpensive. A single computer can run multiple programs to control many processes, and each device is identified and communication is controlled. This is a basic layout of how all these things